So the mechanism, it's an electrophilic mechanism. Remember, an electrophile is something that loves electrons. It's something that's going to be have at least a partial positive charge. What we see is if we try to chlorinate benzene without a catalyst, it happens very, very slowly. But if we add this catalyst of iron chloride, it happens very rapidly. And what happens is this. Chlorine itself, the molecule, is a weak electrophile. It's not really strong enough to do anything here. But when it makes a complex with the iron chloride, that causes this bond to be polarized. It doesn't break it, but it's pulling the electron density over here, and so now this chlorine atom has a partial positive charge. That makes it a stronger electrophile. It's more in search of electrons. This is an electron density illustration of the benzene molecule, and we see that there's a lot of electron density right here in the center of the molecule. So this guy right here is the electrophile that's going to get involved with benzene. The electrophile, oops, what am I doing here? The electrophile is going to bind to one of the carbons in the ring. So this is where the Kekulé structure is useful, because we can picture these two electrons from that pi cloud coming out and attacking this chlorine atom and making a sigma bond with the chlorine atom. These electrons go over here. They were mostly on this chlorine anyway. They go over here, and so we end up with this FeCl4 guy that goes away, and we don't often write him because we don't care about him. We're looking at this part. So now we've got chlorine that has added to this carbon, and there's still a hydrogen here. And because these two electrons came out to make this bond, we now have a carbocation. Because that carbon is short one electron. And this is called a benzenonium ion. It's a carbocation. And now this carbon is now sp3 hybridized. Remember we said the carbons in benzene are sp2 hybridized. This one is sp3 because it's now bound to 4 different atoms. This benzenonium ion is stabilized by resonance. So here's the cation. The electrons from this bond can flip over here, which causes the positive charge to be moved to this carbon. And this one can flip over here, and that causes the positive charge to move over here. And so we have a resonance hybrid of these carbocations. This resonance stabilizes it, and yet this carbocation is still much less stable than the starting benzene ring. The starting benzene ring is much more stable. Then the substitution is completed by losing this proton, this hydrogen ion. So there's a chlorine around, and it shares 2 electrons with the hydrogen and pulls him away as HCl. And then the 2 electrons from this carbon-hydrogen bond return to the benzene ring. These are the electrons that came out of the ring, and these 2 electrons now are going back to the ring. So it's not the same electrons, but nobody cares about that. They're so tiny, they're just interchangeable. And so now we have an aromatic ring again. But we've exchanged, we took a hydrogen off and we put a chlorine on. And so this is the overall mechanism. Here's the benzene plus an electrophile. The electrophile is added to one of the carbons, generating this resonance stabilized carbocation. And then the hydrogen ion comes off, and there you have your substitution. So that's the general mechanism. Here's an energy diagram. So here's the reactant, benzene, and here's a transition state of the electrophile approaching it, and then when it actually bonds, we have this intermediate. So there's an activation energy to get up to here, and this is an endothermic process. It requires energy to be put in, and the reason for that is we've lost the aromaticity of that carbon ring, the benzene ring. And so that causes this to be much higher in energy. And then you have another little hump to get over before you form the product. But this then is an exothermic process, and we end up with this product being a little bit lower in energy than the reactant. And if that were not the case, the reaction would not happen. The reason we have this big down is because we're restoring the aromatic nature of that ring. And that's a big bonus energy-wise.
Would the overall reaction not be endothermic because it's lower in energy?
The overall reaction is endothermic because it's lower. Remember, exothermic is energy going out. So the fact that the products are a little lower in energy than the reactants tells us this was an exothermic reaction. So then your book goes through the specific types of the substitution reactions. And let's look at the halogenation. Halogenation, you've got chlorine or bromine being introduced, and iron halide is the catalyst. Here's the bromination, the bromine, and instead of iron chloride, we've got iron bromide. But the same thing happens. We're exchanging a hydrogen for whatever we're wanting to put on. It's possible to do fluorination, but it requires some other methods. Nitration. Here, sulfuric acid is the catalyst. And what sulfuric acid does is it protonates the nitric acid. So here we've got the nitric acid. It becomes protonated, and then it loses a water molecule and forms this nitronium ion. Here we've got nitrogen with a positive charge. This is a strong electrophile. And so this strong electrophile is going to do what the chlorine did for the chlorination. So here's the NO2 with the positive charge. Pi electrons, program's acting up again. These electrons are going to come over to this electrophile that loves electrons, forming a bond for the NO2. Then this carbocation is actually delocalized over 3 different carbons, that one, this one, and that one. And then the final step is that these electrons in the carbon-hydrogen bond come into the ring, the hydrogen is lost, and now we have nitrobenzene. The mechanism is the same for all of these additions. It's just different what you're adding. What the electrons are doing is exactly the same. Sulfonation. The electrophile is either SO3 or SO3H+. And here we see that this sulfur is an electrophile. And so we end up with the SO3H on it, and this is called benzene sulfonic acid. Benzene sulfonic acid is a strong organic acid, and that can react with sodium hydroxide in an acid-base reaction and form phenol. Alkylation, Friedel-Crafts reaction. This is named for 2 scientists who developed this. Here, the electrophile is a carbocation. You can form that carbocation by removing a halide ion from an alkyl halide. So here we have ethyl chloride. And if we take the chloride off, we take the chlorine off, then we get the ethyl cation. Or you can take ethylene, an alkene, and add a proton to it, and then you'll also get a carbocation. So this carbocation then is the electrophile. The electrons from one of these bonds come and attach and make a single bond. The carbocation is delocalized over these other carbon atoms, and then the electrons from the hydrogen-carbon bond go to the ring, the hydrogen is lost, and here we've got ethylbenzene. Do you see the pattern of how they're all doing the same thing? It's just adding something different each time. But the pattern of what the electrons are doing is the same. In terms of how to learn things like this, drawing it out is really the best thing I can recommend. Just copying it down and drawing, okay, the electrons are going here, the electrons are going there. And after you do that a few times, it should start to make more sense. We can also have acylations, and in which the electrophile is an acyl cation. We have not talked about those much, so I'm not going to talk about it much here either. But you can add an acyl group and you get an aromatic ketone.